Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Dear students, BS Physics, Semester 1, Mechanics 1, Course Code, Physics 1103, Lecture number 17. This is the last lecture of this chapter. Chapter number 5, the Newton's Laws of Motion. The name of lecture is Some Applications of Force and Force of Friction, or simply the phenomena of friction. Dear students, I am talking to you, Rashmat Ali, Assistant Professor of Physics, Khwaja Fareed Government Postgraduate College, Rahimia Khan. Dear students, the material of this lecture has been taken from the book as recommended by the university on your outline of course. The book named as The Physics for the Scientists and Engineers by Survey Javed. The second book is Fundamentals of Physics by Halliday and Resnick and Joel Walker. First of all, the main contents of this lecture, as the name of our lecture heading is given above, some applications of Newton's laws of motion. The other, objects experiencing a net force, forces of friction, forces of static and dynamic friction, kinetic friction, laws of friction. This is the main title diagram of this chapter. So, we are starting the lecture, Some Applications of Newton's Laws of Motion. We have studied the three laws of motion. First law represents the absence of force. Second law represents the presence of force. And the third law represents the property of force and the response of body on which the force is acting. So, before going to the detail of this lecture, we must consider the two cases here. First case is the body is in equilibrium when acceleration is 0. That is, the body is at rest or moving with uniform velocity. Probably this case refers to the first law of motion. Secondly, the body is moving with acceleration A is not equal to 0. In other words, the body has increasing or decreasing velocity. So, when we apply Newton's laws to an object, it means that we are interested only in external force that are acting from outside the bodies. So, first we assume that the objects can be modeled as a particle, whether they are big one or small one. And we see there the friction and their forces. Let's say that objects, there are so many examples. We also consider that the objects can be modeled as particles, the effects of the friction are neglected. This is equivalent to stating that the surfaces are frictionless. Usually the mass of any rope, string, or cable involved are neglected. So we only consider the masses of objects, not the masses of ropes. In this approximation, the magnitude of force exerted at any point along a rope is same at all the points along the rope. When a rope attached to an object is pulling on the object, the rope exerts a force represented by T on the object, and the magnitude T of the force is called the tension in the rope. First of all, we see that the objects in equilibrium means acceleration is zero. In other words, the bodies at rest are moves with uniform velocity. We consider an example. If the acceleration of an object that can be modeled as particle is zero, the particle is in equilibrium. Basically, this is the definition of equilibrium. Consider a lamp suspended from a light chain fastened to the ceiling. The free body diagram for the lamp shows that the forces acting on the lamp chain are the downward gravitational force Fg and the upward the tension force exerted on the chain by the chain. So we can see from the figure, this is a lamp vertically hanging by a support, and this second figure is the free body diagram that represents the tension in the string along the string in upward direction and weight Fg in the downward direction. This represents the free diagram, only the force representation. Tension in the string, there is upward and force of gravity downward. Two forces acting on the lamp hanging down from the ceiling of by a string. Since acceleration is zero, so we can apply the second law of Newton. These forces are only in vertical direction, so sigma Fx will be zero because no force is acting along the horizontal. The other condition, other part of the equilibrium is sigma Fy equal to zero. If we put the values of two forces acting, since T is in upward direction, so it is taken as positive, and Fg is acting downward direction, so with reference to upward force positive, this will be the negative. As the sum of both these forces is zero, so we can find out the tension force will be equal to Fg, that is the force of gravity. This is the case for equilibrium. Here T and Fg are not the action-reaction force pair because these forces are acting on the same body. For action-reaction pair, it is must two forces be acting on the two different bodies. So, objects experience a net force means so many forces are acting on the body, at least more than two forces, more than single force is acting on the body. So, if an object that can be modeled as particle experiences an acceleration, then there must be non-zero net force acting on the object. Means some forces are acting there. We can understand the above hypothesis by some examples. When one object pushes downward on another object, with a force F, the normal force N is greater than the gravitational force, that will be N would be equal to Fg plus F. As we can see from the figure, this is the diagram shown here. One force is the force of book on the table acting downward, that is the Fg, force of gravity. Another force is normal reaction force, that is acting in upward direction. So the reaction force or force of gravity is in downward direction. Means two forces are in same direction, that is Fg and F, where N is the normal reaction acting in upward direction. We can say that N is the sum of two forces, means gravity is downward acting and the force of hand F is also acting downward. So by combining these forces, we get the reaction of book. The second example, consider a crate being pulled to the right on the frictionless horizontal surface. We can see that a man is pulling the crate in the rightward direction by a string. The force is acting on the body in a horizontal surface. Consider the crate is being pulled towards right on a frictionless horizontal surface. Suppose acceleration of the crate is to be found and the force the floor exerts on it. First note that the horizontal force T, that is the tension in the string being applied to the crate, acts through the rope. The magnitude of T, ta, is equal to the tension in the rope as the free body diagram. In addition to force ta, two forces, gravitational force Fg and the normal force Fn, exerted by the floor on the crate, we can see from the figure. The first figure is the actual figure and the second figure shows the free body diagram. Here XY plane is shown and the force is acting on the body, the crate, downward force Fg, the weight of the body, and the upward force normal reaction and the horizontal force tension in the string. The two forces cancel the effect of each other. If the body moves towards right, it means that two forces, force of gravity and the normal reaction, will cancel each other. Then the net force will be only the force along the string in a horizontal direction. So we can apply the Newton's second law. Sigma Fx is equal to tau and max. So from this relation, we can find the acceleration ax, because in this case, acceleration is not zero, means body is starting its motion, means velocity is going to increase. Ax would be equal to T over m. T means tension, m is the mass of body. If T is constant force, then it means that acceleration is also constant, as mass is always a constant. So Ax equal to tau over m or T over m, that is the tension is constant, means acceleration is also constant. Hence the constant acceleration equations of kinematics can be used to obtain the crate's position x and velocity vx as a function of time, means after some time the final velocity can be calculated. We know the equation of motion along the horizontal would be equal to Vfx equal to Vxi plus Axt, and we have found the value of Ax in above relation. So the final velocity will be the Vxf equal to Vxi plus T over m into T. So for the position, we know xf equal to xi plus vxit plus 1 by 2 axt square. So just putting the value of ax, we get the xf equal to xi plus vxit plus 1 by 2 t over m t square. In the situation just described, we can see from the figure 2 the sum of forces acting on the body, the two forces, as normal reaction is acting upward and force of gravity acting downward against the normal reaction. So we can see the sum of force is 0. So N can be found out. N is equal to Fg. Next topic is the friction. Force of friction. Maybe more forces of friction. Friction is the phenomena that results when two bodies slide over one upon the other. We can define it as when an object is in motion either on the surface or in a viscous medium such as air, means the body is freeling downward or projectile is moving in air, or water such as ball thrown in water or stone thrown in water. There is a resistance to the motion due to the interaction of the two surfaces. This resistance is generally named as force of friction. Forces of friction allow us to walk or to run, and necessary to the motion of wheeled vehicles. It means that without friction we are unable to walk. Without friction we are unable to moving body, to stop the moving body. So it is a necessity. This is the usefulness of a friction. Friction helps us to move the body. Friction helps us to stop the body. When a moving car, if there is no friction in the brake leathers and the wheels, then it is impossible to stop the moving car. So friction is useful here. But in some cases it may be useless. So in short, we can divide a friction into two types. One is the force of static friction, another is the force of kinetic friction. We can easily understand if we perform an activity, or with an example we can see how friction produces and what is the actual meaning of friction. We can perform some experiments. Suppose that two bodies are in contact. We see if the surfaces are smooth and slippery, no friction will be produced. If there is some roughness between the two contact surfaces, then the roughness can produce a friction. Actually, the roughness produces some peaks, odd and even. The peaks of one board and jerks on the other body will lock each other. So friction is produces. We can see from the experiments the forces of friction arises from the nature of two surfaces. Because of their roughness, contact is made only at a few locations where peaks of material touch, as shown in the material view of the surfaces. At these locations, the friction force arises in part because one peak physically blocks the motion of a peak from an opposing surface, in part from the chemical bonding, means spot welds of opposing peaks as they come into contact. If the surfaces are rough, bouncing is likely to occur. Further complications can be analyzed, although the details of friction are quite complex at the atomic level. If we see, all substances are made from the atoms, and atoms are spherical. If a substance is made from the atoms, all atoms join each other, and there are so many jerks, ups and downs, just like crests and troughs in waves. So the surface, even the smoothest surface at the atomic level, becomes a rough surface. We see from the diagrams some cane is to be slided on the surface. Two forces are acting on the can as it is at rest, that is the weight acting downward, and the normal force acting on upward. When an applied force towards right F is acting, friction force Fs is produced that is acting in the opposite direction to the applied force. A small circle we can visualize by microscope or some other high resolved microscope. We can see the surfaces of both the bodies, the table and the can. There are so many ups and downs on two surfaces which interlock each other. We see the diagram second. Here's one thing is new. Fk is the force that is shown against the applied force. Here Fs and Fk, these are two forces of friction. Fs, where S is static, Fk, where K is the kinetic friction. We have used the force of friction, a symbol small f, but in boldface. Boldface due to the force nature because it is a vector, and small s and k, these are the two subscriptions, abbreviations for static and kinetic. We can see the explanation. When we apply the force, we see initially the body's rest. We are going on to increase the applied force. We've seen in the above figure that static force is generated. Means in spite of applied force, the body does not move due to the friction. This also shows as the applied force is increased, the friction force is also increased. At some stage, if we go on increasing the applied force, the friction force is also increases. The first portion of this graphical representation, in which types of friction on the horizontal and the force of friction and its magnitude is shown in the vertical axis. So the first portion, the static region, we are seeing from the graph that as the applied force increases means friction force also increases. If we go on this practice, at some peak, some stage that's shown dotted lines, vertical and horizontal, where they intersect each other. Here the force of friction is maximum. We can say that this is the maximum force of static friction. In the second portion, we see that the graph line is falling down as with the orange color, and at some stage, some height, this is continuous decreasing, means increasing friction. This friction force decreases. But at some stage, we see that force of static friction becomes constant. Here the body is not static, but it started moving after Fs maximum. So this force will be regarded as kinetic friction. Kinetic friction and normal reaction have also their relationship. We have shown here the kinetic region too. So Fk, as we study it later, Fk is mu k into n. We can study from the above figures. Consider a man is working on a garden. He filled a trash can, then tried to drag the trash can across the surface of concrete patio. As in figure above, this is the figure. This is a trash can. Can means some three-dimensional body having some volume to place something in it. The trash can across the surface of concrete patio. This is real surface, not an idealized friction surface. Let an external horizontal force F is applied to the right. The trash can remains stationary if F is small. The force that contracts F is the force of static friction. So this diagram also shows that Fs is equal to applied force. As much we increase the applied force, the static force is also increased. When the trash can is on the verge of slipping, Fs has its maximum value. We can represent it as Fs maximum as shown on the figure. But when force F exceeds Fs maximum, the trash can starts moving in the acceleration to the right. When the trash can is in motion, the friction force is less than the F status. Fs maximum means friction force has been reduced from the point of verge of motion. The friction force for an object in motion is the force of kinetic friction. Fk can be used to represent it. So the net force at that time would be F equal to Fk in the x direction, produces an acceleration to the right. According to Newton's second law, if F is equal to Fk, the acceleration is 0 and the trash can moves to the right with constant speed. If the applied force is removed, the friction force acting to the left provides an acceleration of the trash can in the positive x direction. Newton's second law can help us to find that acceleration. Experimentally, we can find that to a good approximation, both Fs maximum and Fk are proportional to the magnitude of normal force. Some laws of force of friction. From many experiments, some empirical laws of friction, summarized experimental observations, the magnitude of force of static friction between any two surfaces in contact can have the value as can be written as Fs equal to or less than mu Sn, where mu Sn is the coefficient of static friction. It means that Fs is directly proportional to normal reaction. Equal sign shows when body is just to slide, and less than would be when body is at the peak, where the dimensionless constant mu s is called the coefficient of static friction and n is the magnitude of normal force exerted by one surface to another surface. But at some stage Fs equal to Fs maximum, that is mu Sn, this situation is called impending motion. The equality in the above equation holds when the surfaces are on the verge of slipping. So the magnitude of the force of kinetic friction acting on the two surfaces can be mathematically written as Fk equal to mu k into n. Means this another force is aroused. The mu k is the coefficient of kinetic friction. The coefficient of kinetic friction can vary with speed. Some observations more: mu k and mu s depend on the nature of the surfaces, but normally what happens, mu k is lesser than the mu s. We can also see from the previous diagram the graph of force versus friction force are shown in that figure. First, the friction force increases. Secondly, it goes to the peak, then it falls towards the some value. The friction force for an object in motion, force of kinetic friction. Some more laws. Friction are nearly independent of area of the contact between the surfaces. While this provides more points in the contact, this is a table as taken from the survey book, different materials and the values of mu s and mu k for different surfaces. As we have studied that mu and mu s, mu k have the no dimensions, no units. When steel moves on the steel, static friction 0.74 or means 74% friction. Similarly, mu k is the 0.057 and so on. These are different values. Steel and steel, aluminum on the steel on steel, simple example of this, the railway track and the wheels of the train, both are generally made from the steel, so their friction we can see. Aluminum on steel, friction reduces. Copper on steel, friction further reduces. Rubber on concrete, this static friction has been increased. Wood on wood, rubber on concrete, glass on glass, waxed wood and the wet snow, waxed wood on the dry snow, metal on metal lubricated, ice on ice, Teflon on Teflon, synovial joints in humans. The least force of friction, whether it is static or dynamics. Dear students, thanks for listening and watching the video, the lecture with patience. Allah Hafiz.